Here is how to calculate for the amount of work needed to empty a conical tank. The formula we're going to need to use is the integral from the bottom of the tank to the top of the water level, and the equation we're integrating is force times distance with respect to y. Here is the diagram we're going to need to use. It has all the variables in it, with h being the height of the tank, rb being the radius of the tank, rs being the radius of the disk of water that we're integrating, and y being the height of the water in the tank. And in order to get our equation, we have to find the mass of the part, which is density times volume. Density is given as 1,000 kilograms per meter cubed in SI units, and volume is equal to pi r squared dy, since the part that we're integrating is in the shape of a disk. And we could find r by setting rs over y equal to rb over h using similar triangles, and then we find that rs is equal to rb over h times y. Then we have, that's our r variable, so now we have the volume, then we multiply that by the density to get our mass, and then we multiply our mass by 9.8 to get the force, and then in order to get work, we multiply the force by distance, and then that's where we get our final equation that we need to integrate in the integral that I showed before.
An example of work being done to empty a conical cone would be this cone at a height of 5 meters and a radius of 3 meters and water filled up 4 meters high. We then would use our volume of part equation and plug in our values for our equation to look something like this. Next, we'll multiply our equation from before times the density of water, which is 1,000 kilograms per meter cubed. Then we can multiply that equation by gravity, which is 9.8 meters per second cubed. And then we should come out with something of 9,800 pi from those constants, and then multiply that equation by the height of the cone minus the height that the water sits at in the cone. Then our integration problem should look something like this, of 9,800 pi with the limits of 5 to 0.
All right, so we have fluid force, also known as hydrostatic force, on a vertical plate. It is an example of a semicircle. Here's the equation. It's going to be F equals W, integral symbol CD, dy times Ly in respects to dy. W is going to be weight density, dy is going to be depth of the fluid at y, and Ly is going to be horizontal length at y.
d of y, not to be confused with dy, is depth. That's the water level throughout the plate. It has to be a positive number within the limits of the integral. Luckily, in this case, d of y is just negative y. Under the x-axis, we plug in any y value and it turns into a positive number. L of y is the horizontal length of the shape in terms of y. A semicircle on a graph is split by its left and right side, so you have to double the equation to get the top of the semicircle. And the integral will not capture the bottom of the semicircle.
Here's a quick example. So the green right here is going to be W equals 9,800 nm cubed. That's going to be the standard weight and density for water. So in this case, it's going to be kind of constant for the problems that we're going to do. The blue in here is going to be dy equals negative y. So then if you look at the graph, it's going to be equals negative parentheses negative 5. So it's that blue line right here because it goes down to negative 5 just at the depth that the plate is. And then Ly is going to equal 2x right here. And then here's the actual equation. Since you got to convert y to x, but in another example problem later on, we'll show you how to do that and how to go in depth into that. And the limits will be negative 5 to negative 2, and we integrate them in respect to dy.
Hi, my name is Francis, and here's my setup for fluid force on a semicircle, which Jesus explained to you. I figured I could use trig sub because u sub wouldn't work. I had to wrestle with this a little bit. I had to alter the substitution to be able to replace both y and y plus 5. After that, I split it up into u sub and the power reducing formula for cosine. Here I converted theta back to y, which I'm sure you know how to do, and I ended up getting 516,321 newtons. The calculator got a slightly different decimal than me, but pretty close, so I think I did okay.